algorithm analysis. It is a mathematical framework which is to analyze the algorithm. And we say Tn, which is the time complexity of an algorithm, is BigO. That means that order of or BigO notation of Fn. And this is shown when there are positive constants such as C and N0, such that Tn is smaller than C times Fn, smaller or equal to C times Fn. Let's see on the graph. This is our algorithm. Sorry, this is Tn, which is our time complexity of our algorithm. And this is the upper bound. That means that for an input size of N0, and when there are more input than N0, the CFN always dominate the Tn, as we can see. It is the time, this axis is time, and it takes more time than the Tn, as we can see. Let's just take this N for that specific N. Look at the y-axis, which is higher than the Tn. But when it is smaller than the N0 in that area, on that region, we can see that this algorithm, which is the CFN, the upper bound, is smaller than the red one, which is our algorithm. But when it is higher than the N0, which is this case, higher than the N0, then the upper bound is dominating. As we can see that when it goes to infinity, or when it goes bigger and bigger, then even in some cases, our algorithm has more time. But when it goes to more input size, in the end, the CFN, which is the upper bound, is dominating than our algorithm. This is the mathematical framework of the BigO notation. It is different. It is the omega, which is not BigO, and it is the lower bound. It is the, as we can see, this is the red in here, but this, sorry, the BigO notation, red, sometimes our algorithm can take more time, as we say, but in this time, in that one, when it is smaller than N0, our algorithm has lower time, but when it goes to bigger input sizes, then it gets, our algorithm gets more, takes more time than the lower bound. As we can see, for the lower bound, it says that when it goes to bigger input sizes, our algorithm dominates in terms of the time complexity. As we can see, let's take this vertical line. If we compare them, as we can see, in that higher input size, let's say it's N1, okay? In that one, the lower bound is lower than our algorithm, and our algorithm takes more time than the CFN. So it means that it is the lower bound, it is lower of our algorithm when it says when it is higher than some N0, which is N0. But before the N0, there is a change in here because our algorithm takes less time than the lower bound, but when it is higher than N0, after that, red is higher, and they are changing, as you can see. So because of that, this condition is important. So if we just find just one C and N0 pair, then we can say that this is false. This inequality is whole. Okay, so we can move on, I think. And this is the theta of N, theta of Fn. When it is the lower bound, sorry, the upper bound, which is BigO, and the lower bound, which is omega, is the same. It is the same order. as we can see in here. In that one, they are, which is the upper bound. This one is the upper bound, and this is the lower bound, and this is the our algorithm, and these are so close to each other, and we can say that its lower bound, which is this one, and upper bound are the same, and all of them are the same. Then when its upper and the lower bounds are the same, then we say that it is the theta of fm. It just simply says that my upper bound and my lower bound are the same, which means also that it is the theta of fm, which is the orders. Is the algorithm orders.